Hello, welcome back to the Shock Show. We are on episode number 6, and I want to get to in this episode a comment from one of the previous episodes. I think it was either one or two, around material properties for finite element analysis. I've been asked this question many times in whatever prototyping or FEA analysis that's done for ultrasonic devices. The question always comes up is, am I using the right material properties? That's a very perhaps a loaded question. There are simple ways to attack the problem. There are complex ways, which maybe are too complex, perhaps because they don't represent reality. And there may be a middle ground somewhere there. And I hope that the approach that I'm going to be talking about today is going to be a little bit of the middle ground, giving you some of my philosophy around the subject, as well as the way to do it. So the way to get material properties. And the interesting thing is that when you're supplied with a supplier's data sheet for your piezoelectric material, you don't get all the material properties. So that's another concern, is that the anisotropic material properties are all not presented to you. So there is a challenge and difficulty to understand if you have the right properties. So the first part of my philosophy on using material properties for FEA is to understand that simulations are for experiments. So what does it mean that simulations are for experiments? So the reason that you do a simulation is that you can have a very high chance of succeeding at experiments. The simulation itself, especially in the initial stages, has limited utility for important optimization. So the problems that exist in your final device is not likely to be caused by not getting your material properties correct. So the problems could be variability, there could be a failure point, there could be lack of performance, but it's not due to just having the wrong property. You had 10% off or 5% off here and there, or you chose the stock material from the FEA program's library versus using all custom filled in values. That's not the reason why your prototype is not going to work. Your prototype is not going to work because there's fundamentally something wrong. I'm assuming that you simulated it correctly using, let's say, a base material properties that were given for the material choice. So you do still need to use the right material choice or class. For example, PZT4 or 8 for ultrasonic power applications, and PZT5, the soft PZT for actuator or in sensor applications. But there's limited stock that you should take in understanding and taking literally, being literal about what FEA is giving you in terms of what you're going to find experimentally. So simulations are for experiments. Once you've done your proof of concept FEA, then you go into your proof of concept experiment. And then you obviously have to recycle that information. What was the difference between experiments and simulations? Then you can do some amount of tuning to come up with a more robust model. But that effort sometimes is kind of goes around in a circle. Like you change properties or you change things about your structure just to match, or you change things about your model just to match your just to match your experiment. That sometimes leads to inexperienced engineers doing things which are incorrect. For example, doubling the piezoelectric charge coefficient because you had twice the displacement experiment, or you had half. So you cut that value by half. That's not the correct approach. There's more likely something much more fundamentally missing from that approach. However, it's not incorrect to use that FEA model, even with perhaps someone who's less experienced and doesn't know how each knob of the model should turn out in the experiment. They can still do that modal analysis, still understand where they need to put their piezos, and then kind of iterate from there. So it's really just a step. And then so if you can imagine a building and you want to get inside the building, that's the purpose. to do whatever, file your car registration, go shopping for groceries. What else do we do? Send a package, whatever you're trying to do. There's a step to get in the door, and that step sometimes is FEA, but the door, the actual building, what you're doing inside, that's the experiments. That's where the real meat is. So I believe taking FEA for that approach is important. The next part that FEA doesn't simulate is variability, right? Variability is something that you can do in finite element analysis. You can, do tolerance analysis, change properties, and whatnot. But practically, the variability you'll see in experiments, and you'll kind of get a false idea of your optimization, because a finite element analysis doesn't account for the large variability which exists, which isn't perhaps explained 100% by material property variation. It's ultrasonic power transducers. They have many interfaces. So interfaces play a huge role in the propagation of acoustic waves and losses in material. So there's something in things in experiments which aren't represented well at all in finite element analysis. So kind of don't kid yourself with, different types of contacts and, optimizing a one type of parameter and another and trying to get the two to match. The real story is so the aspect I'm talking about right now, the variability that you're going to see in experiments is going to far exceed what you will understand in your finite element analysis. Also, material properties for piezos can vary 20% at times. So you then optimize your device to achieve a certain performance, and then suddenly that 20% is lost, for example, when you're actually going to practice. So the next part I want to get into is the practical side. How to match material properties. So there are several steps in order for you to actually take a sample. Let's say you receive a piezoelectric disc, and you want to utilize the properties from that disc or from that you achieve from a data sheet in order to populate the entire matrices of piezoelectric material properties. So basically, this step is basically how do you get a little bit closer. Okay, so I explained in the first part of the video that you can use the basic material properties. Any material that's similar, you just plug in the values for that, and you kind of move forward, and you want to get toward experiments. But the second part is that, okay, what if you want to get just that one step closer that doesn't perhaps violate the rules of physics by just randomly changing properties in order to get your experiments to fit, or your simulations to fit experiments. So here's the steps how to match material properties. So the first step here is find a full set of material properties with similar behavior. So you have a soft PZT, you find a full set of properties for another type of soft PZT. It's not going to be the same as your material, but it will be similar in terms of properties. And then what we do is we establish our baseline set of properties for our, let's say, our disc. So from a piezoelectric disc, the properties you can easily measure are from electrical impedance sweep is D31. You can find out the Poisson's ratio between the 1 and the 2 direction. You can also determine permittivity. So those are parameters you can determine. Also, again, then the coupling factor. For K31, actually, you can determine that from a disc. So then you have that full material property data set that you've already collected from a different material, and you have your own properties that they're limited, but you have your own properties for your own material. Or you have actually something supplied from a data sheet, which is actually worse. You actually just would rather do simple experiments, let's say on a disk sample that you receive. Sometimes you can't do that because you have a ring that makes it more difficult. But you can still determine D33 and permittivity from a ring, although that being said, so let's keep going. So let's say you get either from the data sheet, you get those base material properties, and you also, let's say if you have a disk, you get coupling factor and a couple of other parameters from that. So you have a basic amount of material properties from your material you want to simulate. So the next thing you do is start creating ratios. So let's say we did that K31 from you know the coupling factor of the 3-1 mode of for your new material. So in order to start that transfer of comparisons, you have to create a coupling factor ratio. So you have the K31 of your material and the K31 of the full data set material you found perhaps from a literature resource that provided all those properties. So you establish those two, you start with those two ratios. You find the ratio, like let's say it's the manufacturer is 0.33 and yours is 0.31. Right. So let's say like the new material is 0.35 and your material that you measured is 0.30. So you come up with that ratio, 0.30 divided by 0.35. So you have a ratio. From that ratio, you apply that ratio backwards. So now you applied it forward to get from your starting material, get from your experimental material to your the data sheet you found. That let's say that has the full properties. Then you use that parameter to extract apparent coupling factors for all the properties of your desired material. So you just apply that ratio in reverse in order to get all the coupling factors. And you do the same thing for compliance and permittivity, that you provide those ratios. You got the ratio of the 3-3 direction of the permittivity, and you apply that ratio in reverse. Now after you find the initial one, let's say your new material is 2200 and the material that you want to simulate has a permittivity 1900, you get that ratio. Then you can also use that ratio to back calculate what the permittivity in the 1-1 direction is going to be as a result for your original material with only a partial data sheet. After that, you calculate the charge coefficient. So you calculate the charge coefficient by the coupling factor squared equals the D coefficient divided by well, it wouldn't be the square. Yeah, it would be the square root in this case. Well, actually, it wouldn't be the square root. There's no square root here. Let's just erase that there. Okay, there's no square root because it's squared. So D squared, the charge coefficient squared, divided by the permittivity and the compliance for that specific mode. So from that, you're able to calculate the D coefficient, the charge coefficient. So now you have a material that you have physically sound, basically physically relevant, and permittivity, compliance, and the charge coefficient. Now you can populate your entire matrix using that method. So for the quality factors, and then the final case I want to speak about. So the quality factor here is set to, this is like kind of just basic guidance for the quality factor, is the damping factor. Although you're able to determine, and I just saw somebody posted something in the chat. So after the video is completed, please post that in the comments so I can get to it. I'm recording on my phone actually because it provides better quality than what I would be able to produce from my computer. So put that comment in the chat. Either I'll answer that comment in the comments. So put that in the comments. Either I'll answer your question there, or I'll actually create another video tomorrow talking about it. So I intend to get to all questions and comments and make this kind of a pretty engaged environment. So what I suggest for the quality factor is, firstly, the best thing is to start with it, not with the data sheet, but with actually something you've measured in the lab, because manufacturers' data sheets are kind of they always tend toward telling you the high side of quality factor. They don't tell you the low side of what you're actually going to end up measuring in the lab from their materials. That's what I found practically. They say the quality factor is 2,000, you end up measuring 1,500, like something like that always ends up happening. So you measure it in the lab using your ideal sample, and obviously you may know that the sample size itself it doesn't really matter. But I want to put a point out here is that when you actually apply your piezo sample to your assembly, the quality factor will drop significantly, especially if you are using a glue to attach it. Like the quality factor of PZT4, let's say it's like 600-700, but when you attach it with glue, it ends up being 100 or less at times. So that reduction, that low quality factor, as a result of that glue line, the transfer of energy between the piezo and the structure, that really diminishes the quality factor there. So when you're thinking about the quality factor on damping, you do want to consider the entire assembly when you're doing that. But if you're just considering material properties, and if you were to separate those effects, separate the effects of the material, the piezo material, and the assembly, what you consider, and here's some food for thought. You put 1/3 of the low voltage quality factor. The reason is because as you are when you excite your piezo with anything more than like a volt or a small excitation, the quality factor is going to drop really fast, and that's because losses by domain wall motion in piezoelectric ceramics, especially PZT, are extremely susceptible. They drop extremely quickly due to higher excitation. It's very common for the PZT, let's say, starting at low voltage values of being at 1500. Once you get to higher voltage, resonant excitation, you will actually drop to quality factors of 300 or 500. So very stark, very large drops. So just to note that, because sometimes you simulate something in FEA, you put the data sheet of quality factor of 2000. The simulation just goes wild. You have awesome results. You're right on target for your performance. You build it, and it's like you had a peak like this sharp of displacement when you were doing your FEA, and then you kind of have like something like this kind of low peak when you're doing it in experiments. That happens more often than not. So you want to start to be at least somewhat realistic in terms of your expectations about what your experiment is going to do. So reducing the quality factor by a factor of 3 from what you measure in low voltage, and also using not doing anisotropic loss properties, because loss properties are anisotropic depending on what resonant mode you're working in. Shear, K31, D33, or K33. That's going to change the loss property, but for practical purposes, for your measurement environment that you're actually trying to simulate, that you're trying to get to, the important part is to the important part is to capture the necessary dynamics and the necessary loss, the effective necessary loss factor. So also consider putting a global loss factor for your structure. And also that can also be reduced by 1/3 when you are going for your simulation. It's kind of a bummer that you thought that you would have a really nice loss. You got this PZT4, PZT8 material, only to bond it, and your losses just go skyrocket, and your quality factor drops, and now you're not having anywhere near the performance you thought you would. So just a reality check. And also this also brings to the point where your actual application may be quite complicated. But in order for applying FEA versus experiments and trying to reconcile those two, at least maybe if you're not trying to tune parameters, at least understand the differences, it may be quite overwhelming. So I do suggest that when you're doing experiments, when you're starting FEA and you're trying to understand its translation into experiments, that you do create simple geometry experiments, bonding a disc to a circular plate, or other types of, a simple Langevin transducer, instead of something that's more complicated, has horns, has grooves, has other types of components. It becomes harder to understand the effects, what you should expect in FEA. So also use experiments to create a better system of what you should expect in reality, how much the quality factor drops, how the resonant frequency shifts according to what you have assembled. So you'll be able to at least predict, like if FEA tells me I'm getting 10 microns, I'm actually probably going to get 5, or I might get 12. So you can understand those rules of thumb for yourself, for your simulations. But also, if you're able to really identify and get a little bit closer, not the amount, you want to get plus or minus 20, let's say 20%, that's going to lead you to have a useful simulation. The other thing that you can do is determine the quality factor at high voltage. So the way to do that is using a constant current frequency sweep across the resonance. So if you have your system set up, you can do this using an impedance analyzer. If you have a series resistor, it's a little bit more complicated. This is the topic I'm going to get into in videos to come. So I'm making videos every day, so we're going to get there sooner than you think. The next is if you just stuck with the datasheet, because sometimes you are, honestly. If you're just stuck with the datasheet, just divide that datasheet value by 5. Divide it by 5. Therefore, you will get something similar to what you'll find in practice and high voltage. So thanks for watching this video. It ended up being kind of long, but I think the content was there. I probably could have made this another tomorrow's episode, but I'll think of something new for tomorrow. I just want to let everybody know, thank you for watching this video. You can subscribe to my blog or ring the bell if you want to get the updates for these videos. So what I'll say is, subscribe to the blog. You'll get a general transcript of this video. Just in your email, you'll know when they're all released. It's a more streamlined way. You'll also get my free guide to the top 3 challenges of developing ultrasonic transducers. I see some comments in the chat. I'm not exactly able to answer them as we're going, but if you can leave them in the comments, I'll get to everything. I promise I'll get to everything there. And there's also my email on my website, ultrasonicadvisors.com. So that can be another aspect. Hussein@ultrasonicadvisors.com is a way to reach me if you want to kind of reach out direct. But the email list is also a great way to do some one-on-one, a little bit more private communication on these topics as I release these videos. So thank you for watching. It's already 20 minutes, but I think it was well worth your while. See you next time, which is tomorrow.